Imagine discovering an object that perfectly satisfies the equations of our most successful theory of gravity, and yet the universe refuses to produce even one. White holes are not science fiction inventions. They are not speculative add-ons. They fall directly out of the field equations written by Albert Einstein in 1915. If you take those equations seriously, and physicists do, then white holes are as mathematically legitimate as black holes. And that's the problem, because black holes form naturally. We observe them, we measure their shadows, we detect their mergers. White holes, on the other hand, appear nowhere in the sky. No astrophysical process seems capable of creating one. Worse, the slightest interaction with the universe would instantly destroy them. So here is the tension. If physics allows white holes, why does reality forbid them? To answer that, we need to look at what the equations actually say, not the simplified diagrams, not the pop science versions, but the structure hidden inside spacetime itself. Einstein's field equations are g mu nu equals 8 pi t mu nu. They relate curvature of spacetime, left side, to energy and momentum, right side. These equations are time symmetric. If you replace time, t, with minus t, the equations remain valid. Gravity does not prefer a direction of time. This symmetry is crucial. In 1916, Carl Schwarzschild found the first exact solution to Einstein's equations for a spherical, non-rotating mass. Today, we call it the Schwarzschild solution. Most people interpret this solution as describing a black hole, but that interpretation is incomplete. When you extend the Schwarzschild solution fully, using coordinates introduced later by Kruskal and Sakaris, you discover something surprising. The spacetime contains not only a black hole region, but also a white hole region. Mathematically, the geometry is larger than the simple collapsing star picture. In the maximally extended Schwarzschild spacetime, there are 4 regions: an exterior region like ours, a black hole interior, a second exterior region, and a white hole interior. The white hole is simply the time-reversed version of a black hole. A black hole allows matter to enter but never escape. A white hole allows matter to escape but never enter. Time reversal symmetry guarantees its existence in the equations. And this is the first key insight. White holes are not added by hand. They are demanded by mathematical completeness. But mathematical completeness does not guarantee physical realizability. There are many solutions to Einstein's equations that are mathematically valid but physically unstable. Some violate energy conditions, some require impossible initial states, some collapse under the slightest perturbation. The white hole turns out to be one of the most fragile solutions in all of general relativity. To understand why, we must look at causal structure. In the Schwarzschild geometry, the event horizon is a null surface. Light rays define its boundary. For a black hole, all future-directed time-like and null paths inside the horizon inevitably move toward the singularity. There is no escape. For a white hole, the opposite happens. All past-directed paths originate from the singularity and move outward. Nothing can cross the horizon inward. And this is where instability enters. Imagine a white hole existing in our universe. The universe is filled with radiation, cosmic microwave background photons, interstellar gas, quantum fluctuations. Even a single photon approaching the white hole horizon would attempt to cross inward. But the geometry forbids entry. Instead of peacefully existing, the white hole solution reacts catastrophically. Small perturbations pile up infinitely near the horizon. The solution is not stable under realistic boundary conditions. In technical terms, the white hole region requires perfectly fine-tuned initial data on a Cauchy surface. Any deviation from that data eliminates the white hole and replaces it with a black hole configuration. The instability is not mild, it is exponential. This result appears in perturbative analyses of Schwarzschild spacetime. When realistic infalling matter is included, the white hole horizon transforms into a black hole horizon. The time-reversed solution cannot survive interaction with the thermodynamic universe. And now we reach the deeper conflict. The equations are time-symmetric. The universe is not. Why? Because of entropy. The second law of thermodynamics states that entropy increases toward the future. This is not built into Einstein's equations, it emerges from statistical mechanics. Ludwig Boltzmann showed that macroscopic irreversibility arises from microscopic reversibility through probability. The arrow of time is statistical. A white hole represents an enormous decrease in entropy. Consider a black hole forming from a collapsing star. Matter disperses gravitational potential energy as radiation. Entropy increases dramatically. Black holes have enormous entropy proportional to their horizon area, a result made precise by Stephen Hawking and Jacob Bekenstein. The Bekenstein-Hawking entropy is S equals Ka over 4Lp squared, where A is horizon area and Lp is the Planck length. Black holes maximize entropy. White holes would do the opposite. They would eject highly ordered matter from a singularity in a way that reduces total entropy locally. For that to happen, the universe would need extremely special initial conditions. And this brings us to the second key insight. White holes are not forbidden by equations, they're forbidden by probability. In principle, nothing in classical general relativity stops a white hole from existing, but in a thermodynamic universe, their formation would require entropy to decrease in an extraordinarily precise way. It would be like watching shattered glass spontaneously reassemble into a wine glass, but on a cosmic scale. And that improbability translates into instability. Any microscopic fluctuation destroys the delicate time-reversed configuration. The white hole solution is therefore not dynamically robust. By contrast, black holes are attractors. Many different initial conditions evolve toward black hole formation. Stellar collapse, mergers, accretion, all roads lead to black holes. But no known physical process evolves toward a white hole. This asymmetry is not in Einstein's equations, it is in the boundary conditions of the universe. And boundary conditions matter more than equations. The early universe had extremely low entropy, a fact emphasized repeatedly by Roger Penrose. That low entropy beginning sets the arrow of time. White holes would require the opposite, a high entropy past evolving toward lower entropy. That contradicts cosmological initial conditions as we observe them. So mathematically, white holes are allowed. Cosmologically, they are nearly impossible. This is not yet the full story, because one might argue, even rare, shouldn't quantum gravity allow microscopic white holes to fluctuate into existence? That question forces us to examine the deeper structure of spacetime beyond classical relativity. But before going quantum, we need to understand something more fundamental, the role of global spacetime extension. The white hole region appears only when we perform a maximal analytic extension of the Schwarzschild metric. In realistic gravitational collapse, a star forming a black hole, the extended white hole region does not appear. The physical spacetime formed by collapse is not identical to the eternal Schwarzschild solution. The eternal solution assumes a pre-existing singularity in the past. Real stars do not emerge from singularities. The white hole exists only in the mathematically eternal geometry, not in collapse geometries. This distinction is crucial. Mathematical extension is not physical inevitability. General relativity admits many solutions, but which ones are realized depends on cosmic history. And so we arrive at the central paradox of this video. White holes are perfect solutions, but the universe refuses to initialize them. That refusal may not be a flaw in the equations. It may be a statement about time itself. The instability of white holes is not philosophical, it is mathematical. To see this clearly, consider perturbation theory in curved spacetime. The Schwarzschild metric describes a vacuum solution with mass m. Now introduce a small perturbation h mu nu such that g mu nu goes to g mu nu 0 plus h mu nu, where g mu nu 0 is the exact Schwarzschild metric. For black holes, linear perturbations decay over time. This was shown through the Reg-Wheeler and Zerilli equations. Disturbances radiate away as gravitational waves. The black hole settles into a stable configuration. But when one performs the time-reversed analysis for white holes, the behavior is inverted. Instead of perturbations decaying, they grow toward the past singularity. The white hole horizon acts as an infinite blue shift surface. Any radiation approaching the horizon from the outside becomes infinitely energetic when traced backward in time. That means the white hole geometry is unstable under arbitrarily small disturbances. This is not a qualitative argument. It follows from analyzing null geodesics near the horizon. For a Schwarzschild black hole, outgoing null rays near the horizon experience redshift when escaping. For a white hole, ingoing rays experience exponential blue shift. Mathematically, this comes from the surface gravity kappa, defined for Schwarzschild as kappa equals 1/4m. The exponential factor governing redshift or blue shift near the horizon is e to the kappa t. For black holes, this leads to damping toward the future. For white holes, reversing time leads to divergence. This exponential sensitivity means that no white hole can survive in a universe filled with even minimal background radiation. The cosmic microwave background alone would destabilize it. And this leads to a second mathematical structure that works against white holes: trapped surfaces. In Gevertlian collapse, closed trapped surfaces form when both ingoing and outgoing null congruences converge. The singularity theorems of Roger Penrose show that once such surfaces form under reasonable energy conditions, a singularity is inevitable. White holes would require anti-trapped surfaces emerging from a past singularity. But realistic matter fields satisfying the weak energy condition do not generate such configurations in forward energy evolution. The energy conditions in general relativity constrain stress energy tensors. T mu nu, V mu V greater than or equal to 0 for time-like vectors V mu. These conditions guarantee attractive gravity. Under them, collapse proceeds inward. Time-reversing collapse requires precisely arranged outward-directed geodesic flow. Again, mathematically possible, physically unattainable under natural evolution. So now we have two layers of obstruction: dynamical instability under perturbations, incompatibility with realistic energy-driven evolution. But there is a deeper issue still: the global structure of spacetime. The maximally extended Schwarzschild solution contains two asymptotically flat regions connected by a non-traversable bridge. This structure was analyzed in detail by Martin Kruskal and George Sekaris. In Kruskal-Sekaris coordinates, the metric becomes regular at the horizon. The coordinate singularity disappears. The geometry reveals a full manifold with distinct regions. But here's the key: the white hole region exists only because the extension assumes eternal existence, infinite past and infinite future. Realistic black holes are not eternal. They form from collapse. When a star collapses, the spacetime diagram looks different. There is no pre-existing white hole region. The past boundary of spacetime is regular stellar matter, not a singularity. So the white hole is an artifact of choosing boundary conditions that do not correspond to physical formation scenarios. In other words, white holes are solutions of eternal spacetimes. Black holes are solutions of dynamical collapse. Nature chooses collapse. And this is where cosmic censorship enters. The cosmic censorship hypothesis, proposed by Roger Penrose, suggests that singularities formed through gravitational collapse are hidden behind horizons. There are two versions: weak and strong. Weak cosmic censorship states that singularities are not visible to distant observers. Strong cosmic censorship states that space-time evolution remains globally deterministic, that generic initial conditions do not lead to naked singularities. White holes effectively require a past naked singularity. Their singularity is not formed through collapse. It exists as a boundary condition in the past. This conflicts with the spirit of cosmic censorship.
Although the hypothesis is not fully proven, decades of research support the idea that generic gravitational evolution does not produce past singularities emitting matter. Thus, white holes sit at the edge of determinism. They represent spacetime configurations that require a singularity to act as a source rather than a sink. And classical general relativity treats singularities not as physical objects, but as breakdowns of the theory. That distinction matters. A black hole singularity forms from regular initial data. A white hole singularity is assumed as initial data. There is no known physical process that generates such data. So white holes are not ruled out by local field equations. They are ruled out by global consistency. But what if we go beyond classical theory? Perhaps quantum gravity softens singularities. Perhaps black holes do not end in infinite curvature. Perhaps they bounce. This idea has been explored in loop quantum gravity, particularly by Carlo Rovelli and collaborators. In some models, the black hole interior does not terminate at a singularity. Instead, quantum gravitational pressure halts collapse and causes a bounce. The black hole transitions into a white hole. This scenario preserves unitarity and potentially resolves the information paradox. But the timescales are extreme. For an external observer, the bounce could take longer than the current age of the universe due to gravitational time dilation near the horizon. From the inside perspective, the bounce may be rapid. From the outside, effectively eternal. This quantum picture attempts to rehabilitate white holes as late-time remnants of black holes. However, this proposal is highly model-dependent. It relies on specific quantization techniques and assumptions about the behavior of spacetime at Planck scales. L sub p equals root h bar times g over c cubed. At this scale, classical geometry dissolves. Yet even here, instability concerns remain. Any white hole produced through a bounce must survive interaction with the external universe. If it emits matter, it must do so without immediately recollapsing. And so the same thermodynamic and perturbative issues reappear, now in quantum disguise. Entropy again stands in opposition. Black hole entropy is enormous. S is approximately 10 to the 77th times m over m dollar squared for a solar mass black hole. Reversing that entropy evolution requires extraordinary coherence. Quantum gravity may remove singularities. It does not automatically reverse entropy. And so we face a layered obstruction. Classical instability, thermodynamic improbability, cosmological boundary conditions, and quantum consistency challenges. White holes survive only in equations stripped of context. The moment we embed them in a universe with radiation, entropy, and dynamical evolution, they evaporate conceptually. But this leaves a deeper conceptual puzzle. If Einstein's equations are time-symmetric, and if microscopic physics is largely time-symmetric, why does gravity cooperate so strongly with entropy's arrow? Why do gravitational systems overwhelmingly evolve toward black holes and never toward white holes? The answer may lie in gravitational degrees of freedom themselves. Penrose argued that gravitational entropy is tied to Weyl curvature, the part of curvature not directly determined by matter density. The early universe had extremely low Weyl curvature, highly uniform, extremely special. Black holes represent extremely high Weyl curvature. White holes would represent decreasing Weyl curvature over time. But the cosmological arrow of time begins in low gravitational entropy. White holes would require that arrow reversed. So white holes are not just forbidden objects. They contradict the deepest asymmetry built into cosmic initial conditions. And this suggests something profound. The absence of white holes is not a small anomaly. It is evidence of the universe's temporal structure. Up to this point, white holes have failed because of instability, entropy, and cosmological boundary conditions. But there is an even deeper layer: predictability. General relativity is not just about curvature, it is a dynamical theory of evolution. Given suitable initial data on a space-like hypersurface, the Einstein field equations determine the future and past development of spacetime, at least where the solution remains regular. This idea is formalized through global hyperbolicity. A spacetime is globally hyperbolic if it possesses a Cauchy surface, a hypersurface such that every inextendable causal curve intersects it exactly once. In such spacetimes, evolution is deterministic. Now consider the maximally extended Schwarzschild geometry. It contains regions separated by horizons, including the white hole region. The presence of a white hole implies that part of spacetime originates from a past singular boundary. That singularity is not generated from evolution from regular initial data. It is imposed. This breaks the clean Cauchy development structure. If you attempt to specify initial data on a regular hypersurface outside the white hole, you cannot reconstruct the full spacetime without additional boundary information at the singularity. That means predictability fails unless you prescribe conditions at a non-physical boundary. By contrast, in realistic black hole formation, we begin with smooth stellar matter on a Cauchy surface. The singularity forms dynamically in the future. Determinism holds up to the singularity. White holes invert that logic. They require a singularity in the past that injects information outward. This clashes with the spirit of strong cosmic censorship. While not formally proven in all cases, strong cosmic censorship suggests that generic solutions do not admit Cauchy horizons or pathological past boundaries. White holes effectively demand one. So the issue is not simply instability, it is structural incompatibility with deterministic evolution. Now let's push further into semi-classical gravity. When quantum fields are placed on curved spacetime, the vacuum is no longer inert. Particle creation becomes possible. This is how Hawking radiation arises. Stephen Hawking showed that black holes emit radiation with temperature Th equals h bar kappa divided by 2 pi kb. For Schwarzschild, Th equals h bar divided by 8 pi mkb. This radiation is thermal. It slowly evaporates the black hole. Now consider time reversal. If we reverse the evaporation process, we obtain a white hole absorbing thermal radiation from infinity in a precisely fine-tuned way to reconstruct the original collapsing matter configuration. But thermal radiation is random. To time reverse black hole evaporation, the outgoing Hawking quantum must be replaced by incoming radiation with extremely specific phase correlations. The probability of such a configuration arising naturally is not just small, it is exponentially suppressed by entropy. The entropy of Hawking radiation equals the Bekenstein-Hawking entropy. Reassembling that radiation coherently would require reversing enormous entropic dispersal. So semi-classical effects make white holes even more implausible. In fact, semi-classical back-reaction calculations show that near the white hole horizon, vacuum polarization effects diverge. The renormalized stress-energy tensor, expected value of T mu nu, becomes large due to infinite blue shift of vacuum fluctuations. In black holes, outgoing modes are redshifted. In white holes, ingoing vacuum modes are infinitely blue shifted as one approaches the horizon backward in time. This produces divergences in semi-classical stress tensors. In technical terms, the white hole horizon is unstable under quantum back-reaction. Even if classical general relativity permits it, quantum field theory in curved spacetime appears to destroy it. So now the obstruction is not just thermodynamic, it is quantum. Let us now consider gravitational collapse in reverse from a statistical mechanics standpoint. Imagine a black hole forming from generic matter distribution. That matter configuration occupies a vast region of phase space. Many microstates correspond to similar macroscopic collapse. The black hole state has entropy proportional to area. A white hole would correspond to a very special microstate, one where outgoing matter emerges from a compact region with extremely low entropy correlations. Statistically, the number of microstates corresponding to white hole explosion is minuscule compared to those corresponding to collapse. In Liouville's theorem for Hamiltonian systems, phase space volume is preserved. Time reversal symmetry holds microscopically. But macroscopic irreversibility arises because we condition on low entropy past states. White holes require conditioning on low entropy future states instead. This reverses the usual boundary condition of statistical mechanics. And that is the key insight. The absence of white holes is not due to violation of microscopic laws. It is due to asymmetric boundary conditions imposed on the universe. Roger Penrose proposed that gravitational entropy is tied to the Weyl curvature tensor, C mu nu rs. In a homogeneous Friedmann-Lemaitre-Robertson-Walker universe, Weyl curvature is 0. The early universe was extremely uniform. Low Weyl curvature corresponds to low gravitational entropy. Black holes represent high Weyl curvature concentration. White holes would represent decreasing Weyl curvature over time. But observational cosmology tells us that the early universe began in a remarkably low Weyl curvature state, supported by measurements of cosmic microwave background anisotropies from missions like Planck collaboration. This initial condition defines the arrow of gravitational time. White holes would require an initial state with extremely high gravitational entropy that decreases toward the future. That is opposite of observed cosmological conditions. Thus, white holes are not inconsistent with equations. They are inconsistent with cosmological history. In loop quantum gravity, space-time geometry is quantized. The singularity inside a black hole may be replaced by a high curvature quantum region where repulsive quantum effects appear. Some models suggest that after sufficient internal evolution, a black hole could transition into a white hole. Carlo Rovelli and collaborators propose that quantum tunneling could allow such a transition. The amplitude for tunneling is suppressed by factors related to horizon area. Roughly, probability scales as p approximates e to the minus a over Lp squared. For astrophysical black holes, a over Lp squared is enormous. The suppression is extreme. So even if allowed, such transitions are effectively impossible within cosmological timescales. Furthermore, if such a transition occurs, the resulting white hole must still confront environmental instability. The surrounding universe is not empty vacuum. It contains matter, radiation, gravitational waves. Any emitted material would interact, likely re-triggering collapse. Some models propose Planck-scale white hole remnants, microscopic objects left after evaporation, but these are highly speculative and no observational evidence supports them. And so, after exploring classical relativity, semi-classical gravity, statistical mechanics, cosmology, and quantum gravity, a pattern emerges. White holes are solutions in isolation. They fail in context. The moment you embed them in a realistic universe with entropy, radiation, and cosmological boundary conditions, they cannot survive. Now we push even deeper into symmetry itself. Time reversal symmetry in field equations does not guarantee symmetry in solutions. The equations of motion may be invariant under t goes to minus t, but the space of solutions is partitioned by boundary conditions. This is true in electromagnetism as well. Maxwell's equations allow advanced and retarded potentials, but we observe retarded radiation, waves propagating outward from sources, not advanced waves converging onto charges. Why? Because we impose boundary conditions, no incoming radiation from infinity in the distant past. Similarly, in gravity, we impose a low entropy initial condition at the Big Bang. White holes correspond to advanced gravitational solutions, the gravitational analog of advanced electromagnetic waves. They are mathematically allowed. They are physically excluded by boundary conditions. This parallel is not superficial. It reveals something fundamental. The asymmetry of white holes is the asymmetry of causality. Gravity does not forbid them locally, the universe forbids them globally. In general relativity, Penrose diagrams compress infinite spacetime into finite regions while preserving causal structure. These diagrams make it visually clear what algebra hides. In the maximally extended Schwarzschild spacetime, the Penrose diagram shows 4 regions. Region I, our external universe. Region 2, black hole interior. Region 3, another asymptotically flat universe. Region 4, white hole interior. Region 4 is the white hole. All future-directed time-like geodesics exit from Region 4. Nothing can enter it. But notice something subtle. The white hole singularity lies in the past of region I. That means observers in our region would have a singularity in their causal past emitting matter. This violates the expectation that singularities arise from collapse, not from spontaneous past boundaries. Now let's analyze horizon stability more rigorously. Event horizons are global objects. They depend on the entire future evolution of spacetime. Apparent horizons, however, are local. In realistic collapse, trapped surfaces form dynamically, and the event horizon grows outward. For a white hole, the horizon must shrink toward the past. This means that near the horizon, null congruences must satisfy precise expansion conditions. The Raychaudhuri equation governs the evolution of expansion theta for null geodesic congruences. d theta over d lambda equals -1/2 theta squared plus sigma squared minus omega squared minus Ricci curvature times k mu k nu. Here, sigma is shear, omega is vorticity, Ricci curvature is r mu nu, and k mu is the null tangent vector. Under reasonable energy conditions, null energy condition, r mu nu k nu is greater than or equal to 0. This term drives focusing of geodesics. For black holes, this focusing leads to trapped surfaces and collapse. For white holes, the required anti-focusing would demand violations of typical energy conditions or extremely fine-tuned geometry. Any small deviation in expansion quickly leads to trapped surface formation, effectively converting a white hole into a black hole. This is not speculative. It follows directly from the focusing theorem. Now we go deeper, to Cauchy horizons and determinism. In spacetimes like Reissner-Nordström or Kerr solutions, inner Cauchy horizons exist. These horizons are known to be unstable due to mass inflation. Perturbations falling into such regions undergo exponential blue shift. Energy density diverges. White holes possess a similar vulnerability. Because the white hole horizon is a past horizon, perturbations from the external universe accumulate when traced backward in time. In forward time, this means that even small perturbations make the white hole geometry non-smooth. Semi-classical analysis suggests that T mu nu diverges near such horizons. So white holes suffer from both classical and semi-classical horizon instability. Now let us consider alternative gravity theories. One might ask, perhaps general relativity is too restrictive. What about modified gravity? In F of R gravity, Gauss-Bonn bed extensions, or scalar tensor theories, field equations differ. Additional degrees of freedom exist. But here is the crucial point. White holes arise not from a special feature of Einstein's equations, but from time reversal symmetry and global extension. Most metric theories of gravity preserve local time symmetry. Therefore, they also admit time-reversed solutions. The instability problem does not disappear unless one explicitly breaks time symmetry at the fundamental level. And there is no observational evidence that gravity violates time reversal invariance. So modified gravity does not rescue white holes. Now we push into thermodynamic gravity, the idea that Einstein's equations themselves may be emergent. Ted Jacobson showed in 1995 that Einstein's field equations can be derived from thermodynamic principles, specifically from the Clausius relation delta Q equals T delta S, applied to local Reindler horizons. If gravity is emergent from thermodynamics, then space-time dynamics are deeply tied to entropy gradients. In such a framework, white holes become even more unnatural. They would correspond to spontaneous entropy decrease across local horizons. If space-time geometry is thermodynamic in origin, then white holes are not just improbable, they are thermodynamically inconsistent structures. This pushes the issue beyond geometry into statistical mechanics of space-time itself. Now let's examine holography. In the ADS-CFT correspondence, developed by Juan Maldacena, gravitational dynamics in anti-de Sitter space correspond to unitary quantum field theory on the boundary. Black hole formation corresponds to thermalization in the boundary theory. Time reversing that process would correspond to spontaneous dethermalization, an entropy-lowering evolution. While unitary quantum mechanics allows time reversal in principle, the probability of spontaneous dethermalization is astronomically small. So, in holographic quantum gravity, white holes correspond to extremely fine-tuned boundary states. Generic boundary states evolve toward thermal equilibrium, not away from it. Thus, even in holographic quantum gravity, white holes require non-generic initial conditions. Now we enter perhaps the deepest layer, cosmology itself. Why did the universe begin in low entropy? This is known as the past hypothesis. The early universe was extraordinarily uniform, low in gravitational entropy. This condition explains the arrow of time. White holes would imply the opposite hypothesis, a universe that begins in high entropy and evolves toward lower entropy. But observational cosmology, including CMB anisotropies measured by the Planck collaboration, strongly supports low initial gravitational entropy. White holes are incompatible with that cosmological asymmetry. So what we are seeing is not an isolated prohibition. White holes conflict with horizon stability, energy conditions, semi-classical back reaction, statistical mechanics, holography, cosmological initial conditions, deterministic evolution, and yet the equations remain symmetric. This tension reveals something profound. Time symmetry in fundamental equations does not imply time symmetry in the realized universe. White holes are like advanced electromagnetic waves, permitted but not realized because of boundary conditions at infinity. Their absence encodes information about the global structure of spacetime. Now we move even deeper into quantum information. Black holes pose the information paradox. Does information escape during evaporation? If information is preserved, evaporation must be unitary. Unitary evolution implies time reversibility at the microscopic level. But if microscopic reversibility holds, then white holes must exist as time-reversed black holes. The paradox becomes sharper. Unitary quantum gravity implies reversible dynamics. Macroscopic reality shows irreversible gravitational behavior. Resolving this tension requires understanding how macroscopic irreversibility emerges from microscopic reversibility. White holes sit precisely at that fault line. They are the gravitational embodiment of Loschmidt's paradox. Boltzmann's H-theorem suggests entropy increases statistically, but microscopic laws allow reversal. Loschmidt argued, if laws are reversible, why not observe entropy decreasing? The answer, because low entropy initial conditions bias evolution. White holes are gravitational Loschmidt reversals. They are not forbidden by dynamics, they are excluded by statistical boundary conditions. If space-time itself emerges from entanglement, as suggested in tensor network approaches and ER equals EPR conjectures, then geometry reflects quantum entanglement structure. Black holes correspond to maximal entanglement across horizons. White holes would correspond to decreasing entanglement across horizons. But generic entanglement dynamics in closed quantum systems tends towards spreading, not spontaneous contraction into low entanglement states. So from an entanglement perspective, white holes are dynamically unstable configurations of quantum correlations. They represent entanglement running backward. Thus, at every theoretical layer, classical, semi-classical, statistical, holographic, quantum informational, the same pattern appears. White holes require reversing the entropic arrow encoded in the universe's initial condition. They are mathematically inevitable, but physically disfavored. And this may tell us something deeper than simply they don't exist. It may tell us that the arrow of time is not a small emergent feature, but a global constraint on which mathematical solutions reality selects. Up to this point, white holes have failed because of instability, entropy, semi-classical divergence, and cosmological boundary conditions. Now we ask something more radical. If the fundamental laws are CPT invariant, why does gravity overwhelmingly realize only one temporal orientation of its most extreme solutions? CPT symmetry, the combined operation of charge conjugation, C, parity inversion, P, and time reversal, T, is a deep theorem in local relativistic quantum field theory. Any Lorentz invariant quantum field theory with a Hermitian Hamiltonian respects CPT. Under CPT, a black hole solution should correspond to a white hole solution with appropriate transformations. So if the full quantum gravity theory respects CPT, then white holes must exist in the space of allowed states. The key phrase is space of allowed states, not space of realized states. This distinction becomes sharp in quantum cosmology. Consider the Wheeler-DeWitt equation. H hat psi Hij phi equals 0. This equation governs the wave function of the universe. It contains no explicit time parameter. Time must emerge from semi-classical approximation. In such a framework, the fundamental equation is timeless and symmetric. The arrow of time appears only when we choose boundary conditions on the universal wave function. There are competing proposals for such boundary conditions. One is the no-boundary proposal by James Hartley and Stephen Hawking. In this picture, the universe is finite but without boundary in imaginary time. The wave function favors smooth, low-entropy initial conditions. Another is the tunneling proposal by Alexander Vilenkin, where the universe nucleates quantum mechanically from nothing. In both cases, low initial entropy is preferred. If instead the wave function favored high-entropy initial conditions, white hole-like cosmologies would dominate. But observationally, our universe began in an extremely special low-entropy state. That single empirical fact eliminates white holes at cosmological scale. Now consider a more exotic possibility: baby universes. In certain semi-classical and quantum gravity scenarios, black holes may spawn disconnected regions of spacetime, sometimes described as baby universes branching off. From the internal perspective of that baby universe, the origin might resemble a white hole, an expanding geometry emerging from a high curvature region. But from our perspective, no white hole appears. The branching is hidden behind the horizon. So white hole-like behavior might exist in causally disconnected regions, but not in our observable domain. This reframes the question. White holes may not be globally forbidden. They may simply be causally inaccessible. Now let us push into ADS-CFT again, but more technically. In anti-de Sitter space, eternal black holes correspond to thermofield double states in the boundary conformal field theory. The dual state is sum over n e to the minus beta en over 2, ket hn at left times ket hn at right. This state is time-symmetric. The eternal black hole geometry contains both black hole and white hole regions. However, generic perturbations in the boundary theory destroy the past white hole region. When the state deviates slightly from perfect thermofield double form, the white hole disappears in the bulk geometry. This is crucial. The white hole corresponds to an extremely fine-tuned entanglement state between the two boundaries. Generic entanglement patterns remove it. So even in holography, white holes are measure zero states in Hilbert space. They exist, but only under precise correlations. In charged or Reissner-Sturm and rotating or Kerr solutions, inner horizons act as Cauchy horizons. These are surfaces beyond which predictability fails. Studies show that such horizons are unstable under perturbations due to mass inflation. Energy densities diverge. White hole horizons behave similarly in reverse time orientation. This suggests a general principle. Horizons that separate causally pathological regions are generically unstable. White holes are exactly such pathological separators. Now consider entropy bounds. The Busso covariant entropy bound constrains the entropy passing through null hypersurfaces. White holes would involve entropy flowing outward from a compact region in a way that potentially saturates or violates such bounds. No known realistic process respects these bounds while producing a white hole. Again, not forbidden by local equations, but disfavored by global entropy accounting. In eternal inflation scenarios, spacetime volume grows without bound. Probabilities must be defined using a measure. Under typical measures, low entropy states are exponentially suppressed compared to high entropy configurations. Yet we observe low entropy. This is the measure problem. If the measure favored high entropy generically, white hole-like universes would dominate. They do not. So the absence of white holes is connected to the same mystery as the low entropy of the Big Bang. These are not separate puzzles. They are reflections of the same asymmetry. Now let us address CPT-symmetric cosmologies. Some proposals suggest that our universe has a mirror counterpart extending before the Big Bang, a time-reversed partner. In such a model, what appears to us as a low-entropy beginning is a central symmetry point. The opposite temporal direction may contain structures that resemble white holes relative to our arrow of time. These ideas have been explored by researchers like Neil Turok in CPT-symmetric universe models. In that picture, white holes might not be absent. They may exist in the time-reversed half of the full spacetime, but within our temporal orientation, we would never observe them. Again, boundary conditions dominate. Now we confront the deepest conceptual layer. The Einstein equations are local differential equations. The arrow of time is a global condition. White holes are casualties of global constraints imposed on local laws. This reveals something profound about physics. The laws do not fully determine reality. Initial conditions complete the story, and initial conditions break symmetry. White holes are mathematically democratic. The universe is not. In the path integral approach to quantum gravity, one does not ask which single spacetime occurs. Instead, one sums over all possible geometries. Formally, the gravitational partition function is written schematically as z equals integral dg e to the I s sub g over h bar, where s sub g is the Einstein-Hilbert action, s equals 1 over 16 pi g integral r the root of negative g d4x. In principle, every geometry compatible with boundary conditions contributes to the amplitude. White hole geometries are valid classical saddle points of this action, so they are not excluded from the path integral. But here is the crucial point. Contribution to the path integral is weighted by the action. In semi-classical approximation, the dominant contributions come from stationary points of the action, classical solutions, but their weight depends on the phase and boundary conditions. If we impose boundary conditions corresponding to low entropy in the past and open radiation in the future, the dominant saddle points are black hole-forming geometries. White hole geometries would require boundary conditions specifying highly correlated outgoing radiation in the future. Such boundary conditions correspond to extremely fine-tuned quantum states. In the language of the path integral, white holes are not forbidden, they are exponentially suppressed. Their amplitude is not zero, it is effectively negligible. Now let us move to Euclidean quantum gravity. In Euclidean methods, one rotates time to imaginary values. T becomes I tau. This transforms Lorentzian metrics into Riemannian ones. Black holes become smooth geometries with periodic Euclidean time. The Euclidean Schwarzschild solution is regular only if Euclidean time has period beta equals 8 pi m. This periodicity encodes Hawking temperature. Black holes appear naturally as thermal saddle points in Euclidean gravity.
White holes, however, do not have independent Euclidean counterparts. The Euclidean solution corresponds to the full Kruskal extension, but thermal weighting favors black hole thermodynamics, not entropy-decreasing white hole processes. In thermodynamic language, black holes are equilibrium objects. White holes are entropy-lowering fluctuations, and entropy-lowering fluctuations are suppressed by factors of e to the minus delta s. For astrophysical black holes, delta s is enormous. So Euclidean gravity reinforces what classical thermodynamics already suggested. White holes are allowed, but statistically invisible. Microscopically, quantum evolution is unitary and reversible. But macroscopic irreversibility emerges through decoherence, entanglement of subsystems with the environment. When matter collapses into a black hole, the system becomes entangled with gravitational and quantum degrees of freedom. Information disperses into correlations that are practically impossible to reconstruct. To produce a white hole, one would need to reverse not only the classical collapse, but the full entangled quantum state of the environment. This is not forbidden by unitary evolution. It is forbidden by practical impossibility.
Decoherence ensures that phase information becomes distributed across inaccessible degrees of freedom. White holes require recoherence of that information. The timescale for spontaneous recoherence in macroscopic systems grows exponentially with entropy. For black holes, entropy is proportional to area, and area scales as mass squared. For stellar mass black holes, entropy is on the order of 10 to the 77 in Boltzmann units. The probability of spontaneous entropy decrease of that magnitude is effectively zero over cosmological timescales. So decoherence translates statistical suppression into physical non-occurrence. White holes are Low-Schmidt reversals in a decohered universe. They require reversing entanglement across astronomical numbers of degrees of freedom. Now we arrive at the deepest conceptual synthesis, the relationship between entropy and causal structure. Causal structure defines what can influence what. Entropy defines the direction in which typical states evolve. In general relativity, horizons encode causal asymmetry. In thermodynamics, entropy encodes temporal asymmetry. White holes violate both simultaneously. They reverse entropy flow and causal orientation. This is why their instability is so universal across frameworks. In classical geometry, they are unstable under perturbations. In semi-classical gravity, vacuum fluctuations diverge near their horizons. In statistical mechanics, they are exponentially suppressed. In holography, they correspond to fine-tuned boundary states. In quantum cosmology, they conflict with low-entropy initial conditions. In decoherence theory, they require impossible recoherence. Every layer of physics points in the same direction. And this convergence suggests something profound. The absence of white holes is not an accident of astrophysics. It is a reflection of how deeply the arrow of time is woven into the fabric of reality. The equations allow time symmetry. The universe chooses one orientation.
White holes are not mistakes in mathematics. They're shadows of a symmetry that reality does not populate. Their existence in equations is evidence that the laws themselves are neutral. Their absence in the sky is evidence that the universe is not. And that may be the deepest lesson here. Physics does not merely describe what can happen, it describes what can happen under specific boundary conditions. White holes sit at the boundary between law and history. They are possible, but only in a universe whose entropy runs backward. And that is not the universe we inhabit.